I'm sorry, I needed to start recording that. So complete change of subject, so we can start recording with the new subject, is the contour integral for this thing that kind of looks like a rational function. So now the problem is to do the integral from 0 to infinity of a fraction. The bottom is 1 plus x, and the top is x to the p minus 1 dx. So this is an integral we came across using the techniques from the gamma function and an already wickety whack in an integral substitution. And so now we would like to do this function. So what we're going to do is we're going to change that to integral over a certain contour, which I'll call C. And just to emphasize that we're changing this to a contour integral, I'm going to change the name of the variable to Z, or I'm sorry, if I'm in Cambridge or Oxford in 1912, that variable is Z now, isn't it? So anyway, and so we have a 1 plus Z on the bottom. Actually, you probably both grew up saying Z.
Yes.
Yeah. When I taught in Canada, I just avoided using that letter because I would just come out, I'd say Z, and everyone in Canada was accustomed to Z. And it's like, oh, okay, we'll use W. Anyway, so we're going to do it over the contour. Now, this is the art of contour integration, and you've seen a couple. That's like a doctor who's seen 2 livers. That doesn't really do you very much. So there is an art to choosing a contour, and the art involves being careful about where the poles are, and so that's already an art in itself. But the other is to find a contour where you can actually do the integrals. And so you know, if you make a contour that has some kind of crazy shape to it, well, you're going to have to use Cauchy's theorem and change it to something. You want circles or you want lines, and that's about as complicated as you want it to be. So, so anyway, let me draw this contour, and it's kind of fun. Oh wait, before I do that, let's look at the residues here. So, so I've got z to the p minus 1 over 1 plus z. And as far as we're concerned, this is pretty good. It only has one pole, and the pole's at z equals minus 1. And this gives us a warm fuzzy feeling because the integral that we're looking at is from 0 to infinity. So minus 1 is nowhere near the integral that we're doing. And that's the other crazy thing about complex functions. And it's also, to an extent, a crazy thing about harmonic functions is you're going from 0 to infinity. You're not going to go anywhere near where z is minus 1. But that actually determines what's going on. That these things spread out. I mean, kind of once you know one point, that's not quite right, but pretty close. 1 point in a residue, then you have the Cauchy formula. And so anyway, so the only pole is z equals minus 1. And you guys get to say I told you so. The easiest way to get the value of the residue there, because the top is kind of wickety whack, the top some x to some transcendental power. So the easiest way to get at the residue there is to use the derivative formula that you all are so fond of, and that I didn't quite make fun of it, but I said, oh, I never use it. Well, here's a good place to use it. So the residue works out to be e to the pi I. Now you might be tempted to change that to something, but don't. So you take e to the pi I and raise that to the p minus 1 power. So the the P is not going to disappear. P does show up in what the residue is. So, okay. So now we know where the stuff of interest is. I'm going to try to draw this pretty big. So we're going from 0 to infinity. I'm going to put that in red because that's what we're really interested in. And we need a contour, and the contour needs to go around the point -1. So let me indicate where -1 is. That's over here someplace. And so we want a contour that includes that point and excludes any other nastiness that we might come up with. And here's how to do it. And this is something that you can see used in other contour integrals. So and you can't draw this right. So I'll show you in what way the drawing is wrong. But I'm going to take most of a disk of radius epsilon around the origin. We don't like the origin with something like x to the p because we get this branch of logarithm problem. Okay, so we're going to take this disk of radius epsilon, and then what we're going to do is we're going to shoot out along the x-axis, and we got to shoot out at least one, and you'll see why in a second. And then we're going to take a big circle of radius, whatever it is that we shot out to. But we need to make this big circle include -1. And then we're going to shoot back to that little disk of radius epsilon. So let me put some orientation markers in here. So there's the contour C. I guess I ought to label it. So we've got the contour C that is, that's a simply connected region, and it only includes one pole. And so the integral of this function over C, the contour C, is 2 pi I times the pole. And I'm not sure I ever wrote that down anywhere. It'll come up in a second. Okay. So, I think this is it. So I can say what this integral is. I'm going to write it over here. It's 2 pi I. There's only one pole. So instead of the sum of the residues, it's just the residue. So that's e to the pi I, and then e to the pi I is raised to the p minus 1 power. So as far as doing this z contour integral, yeah, we can do that. I mean, there's an awful lot that we've gone into that goes into why we can do that, but we can do that. And so we get an actual number that is made up of numbers that are familiar to us. And so that is a nice, warm, fuzzy feeling. If p is a whole number, then we've got -1 to a whole number. And that's something, so that's either plus or -1. So when p is a whole number, this residue, I'm sorry, this integral is plus or minus 2 pi I. It seems to me I've forgotten. No, I don't remember whether I remembered, so I'm going to remind us. When we're doing this integral, we're only interested in values of p between, where to go, 0 and -1. I'm sorry, 0 and 1. I'm not sure why I said -1. That's to make the integral convergent, right? Because now with these p's, you get more on the bottom, so you get a convergent improper integral. All right. So one of the arts of doing a contour integral is finding the contour. And so the contour includes one residue. So the integral is 2 pi I times that residue. And now there's a couple of kind of standard boilerplate things that happen. So I never labeled these radii. There are 4 pieces to this integral. Oh, I'm sorry, I forgot to say why this isn't accurate. That these two horizontal pieces actually go, they're coincident. One is go over that, that's the positive x-axis, positively, go around the circle, go around, go down the positive x-axis negatively. So there's a gap that's drawn in there, but in fact, there is no gap. So that's where this picture goes wrong. And this is a very typical thing that happens when people are drawing contours in order to do integrals by residue. So there we go. So there are four pieces, and I'm kind of a pictorial kind of guy. So I'm going to say the integral over C is made up of four integrals. I'm not going to write the integrand. I'm talking about what happens to the integral. And so there's what's going to be. And for the first one, the domain is the horizontal line shooting in the positive direction. And then we're going to go around the circle. I'll come back to that. For the third one, the domain is the horizontal line shooting in the negative direction. So instead of giving it names, it's going to be pretty clear what's happening soon. The third one is the big circle, and that's done counterclockwise. And the fourth one is the little circle. That is so little that I can't get it to come out. And so, okay. And this is the standard thing that happens. It's pretty much, this is a rule of thumb. So don't quote me on this, but think of it as a way to do some things, which is when you do a contour like this, the big circular parts, as long as you have a convergent integral that you started with, that means the real integral. So I'm saying because this integral converges because of this condition, that the stuff that happens way out here for high values of r, when we're doing this as an improper integral as we properly should, that goes to zero. Otherwise, this won't converge. And the same thing with the little smaller circle, the integral over that part goes to zero because there's nothing there. There's no pole there or anything, right? You're integrating some number over a circle of radius zero. Now I should be saying take the limit, blah blah blah. But so the integrals over the circular portions vanish. And unless you do something really wickety whack, and that would just involve pretty much starting with an integral that doesn't converge. I'm not saying that's the only way, but I'm saying that's a typical way. As long as this integral converges, then the integral of the corresponding complex function over this big old circle, that's got to be zero. So, so that just goes to kind of the geometric nature of integration. Okay, so I am going to not fuss about those at all, and because I know from the general setup of the situation that those integrals vanish as in the limit. So we got to take the limit as epsilon goes to zero, and got to take the limit as r goes to infinity, and so those integrals vanish. If you can think that way about integrals, that will help you simplify a lot of problems. So, okay. So now what we're seeing as far as what's left over is the integrals that matter in this problem are, so I'll just say this is what matters. One is the integral. This is the horizontal shooting off to infinity part. So that's the integral from epsilon to infinity. Now that's a double improper integral. We should be doing a lot of more formal stuff that's going to come out exactly the way that you think it's going to come out. Well, we can parametrize that, I guess. Well, it's just that's fine. It's already parametrized. So x is the parameter, and we've got 1 plus x on the bottom, and x to the p minus 1 on top. Now, I have not, this is not a change of variables. This is, excuse me, this is, I started with the x integral turned it into a contour integral over z, but now when I'm integrating over this horizontal piece, well, the parameter for that is x, so we're back to x. Now, there's something funny that happens to x as you go around the circle. Again, this is something that you would expect with a lot of contour integrals. So the next thing is going to be the integral from infinity to epsilon. So this is coming back home from infinity to epsilon, and the bottom stays the same, but on top, what's happened is in going around the circle, the argument has been increased by 2 pi. You've gone around the circle, so you've added 2 pi to the argument. So what you get on top here is x times e to the 2 pi I. That takes care of the change in argument. And then you raise that whole thing to the p minus 1 power. Again, a typical kind of thing that happens with contour integrals. And so there's our situation. So now what we have here is we've got an e to the 2 pi I to the p minus 1, which is, that's just a number. So that comes out of the second integral. So what we have here is 1 plus e to the 2 pi I to the p minus 1, or 2 pi I p minus 1. So this is the factor that comes out. I've got the same integral twice. And so what we're left with is integral 0 to infinity. Is there a factor of 2 in here someplace? No, I don't think so. Fraction 1 plus x on the bottom, x to the p minus 1 on top, dx. And we know what that is because, well, that's the integral that we're looking for. So we know what that is because we've done the residue thing. And so what we have is that the integral from 0 to infinity of that fraction, top is x to the p minus 1, bottom is 1 plus x dx. That's the integral that we were looking for, is the 2 pi I times the sum of the residue, 2 pi I e to the pi I, oh darn it, e to the pi I times p minus 1. That's all one thing in the exponent. So there's the top. And we're going to divide that by 1 plus e to the 2 pi I times p minus 1. Now that's just a number. It's a complicated number, but it's just a complex number. But we can simplify that a little bit. And it takes a little bit of elementary algebra to do this. But what I'm going to do is multiply top and bottom by e to the minus pi I to e to the minus pi I p minus 1. So I'm going to take this thing on top and I'm going to multiply by its reciprocal. And so what that gives is just a it brings out a factor of 2 pi I times a complicated fraction 2 pi I over e to the minus pi p minus 1 plus, no, it should be minus e to the plus pi I over p minus 1. I'm sorry, that's written a little small, but it's complicated. And so this is where the little bit of recognition comes in. First of all, a little bit of algebra. On the bottom, you have a common factor of e to the minus pi I. So that just leads to a sign change. And what you end up with is 2 pi I times 1 over the sine of pi p. So using the complex version of sine of theta is e to the I theta minus e to the mi theta. It's a fraction. The top is e to the I theta minus e to the minus I theta, and the bottom is 2 theta, 2i, excuse me, 2i, no theta on the bottom. And so we've got that upside down here. It's kind of hard to read in this, but it's there. So there was an e to the I pi in each of the terms on the bottom here, because you had e to the pi I p minus 1. So you got a pi I p, and then using the exponent laws, that e to the pi I comes out. And that's now that really is minus 1. So anyway, so what we end up with is, I'm sorry, I have an extra I in here. What we end up with is that this integral, this wickety-whack integral that we started with, that if you had stopped me on the street and said, hey, is this useful? Do you think anyone would ever use this? I would have said most definitively no, but but in fact is a useful integral. And I lost the statement here. Hang on. Yeah, pi over sine. I got an extra 2 in here somehow as well. Anyway, integral 0 to infinity of this fraction x to the p minus 1 on top, 1 plus x on the bottom, dx is equal to, and this is when 0 is less than x is, I'm sorry, 0 less than p less than 1, a fraction pi over sine pi p. Now that should scare you if p is a whole number, because some sine pi p's are infinite, but if p's a whole number, that violates this condition here. So so you have this pi over sine pi p. I don't remember ever seeing that in my life in any other context, but that's the deal here. Now there's one other change that we have to do to relate this back to where we started. We had that p was 1 minus m. And so now we come up with this formula, gamma of m times gamma of 1 minus m is, it's a number, but it depends on m in a complicated way. So the top is pi, and the bottom is sine of pi times 1 minus m. Let me put some extra parentheses around that. So we have this insane formula for this product of two gamma functions. And what's really insane about this is the following special value of the gamma function, which is probably worth remembering. And that's what happens when m is a half. Now, when m is a half, the bottom here, that's sine of pi over 2, so that's just 1. So this is pi. So sine of a half times sine of a half is pi. So that means that gamma of 1/2 is the square root of pi. Special value of gamma. And it's an awful lot of work to figure this out. And a real mathematician is one to whom that's as obvious as twice 2 makes 4 is to you. Not. I don't know what kind of person that is, but this is something that, this is kind of a nice calibration for the gamma function, because we know gamma at the positive integer values, and we know gamma at the negative integer values. We don't like it as a pole, but now we've got finally a value of gamma at a non-integer value, gamma of 1/2, and square root of pi. So there's the kind of, I'll call that a calibration step. So I think we should all go to the cricket match now, because we have done our mathematical duties for today, and it's a doozy. I haven't done a calculation like this in, well, since the last time I taught complex analysis. Um, and so it's good to do these every now and then. I just keep telling myself that. So keep telling yourself that. And when we, uh, I think that's about all we got for today. I'm exhausted from doing that. But when we come back, what we'll find is some other properties of the gamma function, and um, and then start to talk about the Riemann zeta function. Where am I? We have some other properties of gamma to talk about, and then this kind of stuff kills a lot of trees. Well, we'll begin to continue to talk about some of these special functions. The zeta function is much closer to my heart, so and so we have to talk about that anyway. That's what I got for today. Does anyone have anything to add or subtract?
Nope. See you.
Okay, I guess I should give you the option of multiplying, but that would be adding or subtracting exponents. So shall we call it good?
Yep.
Okay, so Wednesday, and yeah, I'll obviously I'll scan this, but you really need to kind of go over this. There's an awful lot of detail to this, and in some ways it's kind of fun. So I would highly recommend that. So see you soon.